Newton's third law, action and reaction. Define force as part of an interaction. State Newton's third law of motion. Describe how to identify a pair of action-reaction forces. Explain why the accelerations caused by an action force and by a reaction force do not have to be equal. Explain why an action force is not canceled by a reaction force. Explain how a horse-cart system accelerates. Explain what must occur in every interaction between things. The big idea: for every force, there is an equal and opposite force. If you lean over too far, you'll fall. But if you lean over with your hand outstretched and make contact with the wall, you can do so without falling. When you push against the wall, it pushes back on you. That's why you are supported. Ask your friends why you don't topple over. How many will answer because the wall is pushing on you and holding you in place? Probably not very many people, unless they're physics types. Realize that walls can push on us every bit as much as we push on them. Similarly, kayak paddles that push water backward are pushed forward by water. Can there be only one force in an interaction? Connect the hooks of two spring balances. Have a tug of war with a classmate. Observe the reading on the scales during the tug of war. Caution, don't pull too hard. Try to have one person pull harder than the other. Note the scale readings again. With your classmate, hold two bathroom scales back to back. Now push on the scales and share scale readings. Analyze and conclude. 1. Observing. How did readings on the spring balances compare throughout your tug of war? 2. Predicting. Is there some way for one person to exert a force without causing the other person to interact? Explain. Making generalizations. Why do we say forces occur only in pairs? 7.1. Forces and interactions. In the simplest sense, a force is a push or a pull. Looking closer, however, Newton realized that a force is not a thing in itself. A force is always part of a mutual action that involves another force. A mutual action is an interaction between two things and another. For example, consider the interaction between a hammer and a nail as shown in Figure 2.2. A hammer exerts a force on the nail and drives it into the board. But this force is only half the story, for there must also be a force exerted on the hammer to halt it in the process. Think. Does a stick of dynamite contain force? Explain. No, force is not something an object has, like mass. Force is an interaction between one object and another. An object may possess the capacity of exerting a force on another object, but it cannot possess force as a thing in itself. Later, we will see that something like a stick of dynamite possesses energy. Figure 7.1. When you push on the wall pushes on you. 7.2. The interaction that drives the nail is the same as the one that halts the hammer. What exerts this force? The nail does. Newton reasoned that while the hammer exerts a force on the nail exerts a force on the hammer. So, in the interaction between the hammer and the nail, there are a pair of forces, one acting on the nail and the other acting on the hammer. Such observations led Newton to his third law. the law of action and reaction. Concept check. Why do forces always occur in pairs? 7.2, Newton's third law. Newton's third law describes the relationship between two forces in an interaction. Newton's third law states that whenever an object or one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. One force is called the action force, the other is called the reaction force. It doesn't matter which force we call action and which we call reaction. The important thing is that there are partners in a single interaction and that neither force exists without the other. They are equal in strength and opposite in direction. Newton's third law is often stated: to every action there is always an equal and opposing reaction. Look at figure 7.3 and 7.4. In every interaction, the forces always occur in pairs. For example, you interact with the floor when you walk on it. You push against the floor, and the floor simultaneously pushes against you. Likewise, the tires of your car interact with the road to produce the car's motion. The tires push against the road, and the road simultaneously pushes back against the tires. When swimming, you interact with water. You push the water backwards, and the water pushes you forwards. Figure 7.3, the girl jumps to the shore, the boat moves backwards. Figure 7.4, the dog wags the tail, and the tail wags the dog. Notice that the interactions in these examples depend on friction. For example, a person trying to walk on ice where friction is minimal may not be able to exert an action force against the ice. Without the action force, there cannot be a reaction force, and thus there is no resulting forward motion. Concept check. What happens when an object exerts a force on another object? A point to ponder. 7.3, identifying action and reaction. Sometimes the identity of the pair of action-reaction forces in an interaction is not immediately obvious. For example, what are the action-reaction forces in the case of a falling boulder? You might say that Earth's gravitational force on the boulder is the action force, but can you identify the reaction force? Is it the weight of the boulder? No. Weight is simply another name for the force of gravity. Is it caused by the ground where the boulder lands? No. The ground does not act on the boulder until the boulder hits it. There is simple recipe for treating action-reaction forces. We know the Earth pulls on the moon. Does the moon also pull on the Earth? If so, which pull is stronger? Asking which pull is stronger is like asking which distance is greater between New York and San Francisco, or between San Francisco and New York. The distances either way are the same. It is the same with force pairs. Both Earth and Moon pull on each other with equal and opposite forces. Equal and opposite. First, identify the interaction. Let's say one object A interacts with another object B. The action and reaction forces are stated in this form. Action. Object A exerts a force on object B. Reaction. Object B exerts a force on object A. To identify a pair of action-reaction forces, first identify the interacting objects A and B, and if the action is A on B, the reaction is B on A. Figure 7.5. In the force pair between object A and object B, note that when action is A exerts force on B, the reaction is simply B exerts a force on A. And here are three A and B force pairs. for your perusal. Look at them carefully. So, in the case of the falling boulder, their interaction during the fall is the gravitational attraction between the boulder and the Earth. If we call the action Earth exerting a force on the boulder, then the reaction is the boulder simultaneously exerting a force on Earth. Note, you can't pull on something unless that something simultaneously pulls on you. That's the law. How do you identify the action-reaction forces in an interaction? 7.4, action and reaction on different masses. Interestingly enough, in the interaction between the boulder and Earth, shown in figure 7.6, the boulder pulls up on Earth with as much force as the Earth pulls down on the boulder. The forces are equal in strength and opposite in direction. We say the boulder falls to Earth. Could we also say Earth falls on the boulder? The answer is yes, but the distance Earth falls is much less. Although the pair of forces between the boulder and the Earth are the same, the masses are quite unequal. Recall that Newton's second law states that acceleration is not only proportional to the net force, but is also inversely proportionate to the mass. Because Earth has a huge mass, we don't sense its infinitesimally small acceleration. 7.6, Earth is pulled up by the boulder with just as much force as the boulder is pulled down by the Earth. Although Earth's acceleration is negligible, strictly speaking, it does move up towards the falling boulder. So when you step off a curb, the street actually comes up a tiny bit to meet you. Force and mass. A similar example occurs during the firing of a cannon, as shown in figure 7.7. When the cannon is fired, there is an interaction between the cannon and the cannonball. The force of the cannon exerts on the cannonball is exactly equal and opposite to the force the cannonball exerts on the cannon. So the cannon kicks. On first consideration, you might expect the cannon to kick more than it does, or you might wonder why the cannonball moves so fast compared with the cannon. Figure 7.7, the cannonball undergoes more acceleration than the cannon because its mass is much smaller. According to Newton's second law, we must also consider the masses. Let F represent both the action and reaction forces. M, the mass of the cannon, and M, the mass of the cannonball. Different sized symbols indicate the differences in masses and the accelerations. The acceleration of the cannonball and cannon are. Cannonball is F over small m equals large A, and the cannon F over large M equals small a. Do you see why the change in the velocity of the cannonball is great compared with the change in velocity of the cannon? A tug of war occurs between boys and girls on a polished floor that's somewhat slippery. If the boys are wearing socks and the girls are wearing rubber-soled shoes, who will surely win and why? The girls will win. The force of friction is greater between the girls' feet and the floor than the boys' feet and the floor. When both the girls and the boys exert action forces on the floor exerts a greater reaction force on the girls' feet. As a result, the girls stay at rest and the boys slide toward the girls. A given force exerted on a small mass produces a greater acceleration than the same force exerted on a large mass. If we extend the basic idea of a cannon recoiling from a cannonball in launches, we can understand rocket propulsion. Consider air escaping from an untied, blown-up balloon. If the balloon is released and allowed to move, as shown in figure 7.8, it accelerates as air comes out. A rocket accelerates in much the same way. It continually recoils from the exhaust gases ejected from its engines. Figure 7.8. The balloon recoils from the escaping air and climbs upward. What's the action? What's the reaction? Each molecule of exhaust gas acts like a tiny molecular cannonball shot downwards from the rocket. A common misconception is that a rocket, like the one shown in figure 7.9, is propelled by the impact of exhaust gases against the atmosphere. In fact, before the advent of rockets, it was commonly thought that sending a rocket to the moon was impossible because of the absence of an atmosphere for the rocket to push against. This is like saying a cannonball won't recoil unless the cannonball has air to push against. This is not true. Both the rocket and the recoiling cannon accelerate because of the reaction forces created by the cannonballs they fire, air or no air. In fact, rockets work better above the atmosphere where there is no air resistance. The rocket recoils from the molecular cannonballs it fires and climbs upward. The space shuttle, fascinating shot. Unbelievable. Beautiful. In fact, rockets work better above the atmosphere where there is no air resistance, lift. Using Newton's third law, we can understand how a helicopter gets its lifting force. The whirling blades are shaped to force air particles downward, action, and air forces the blades upward, reaction. This upward reaction force is called lift. When lift equals the weight of the craft, the helicopter hovers in midair. When lift is greater, the helicopter climbs upward. Birds and airplanes also fly because of action-reaction forces. When a bird is soaring, the shape of its wings deflects air downwards. The air in turn pushes the bird up. It's called lift. The slightly tilted wings of an airplane also deflect oncoming air downward and produce lift. Airplanes must continuously push air downward to maintain lift and remain airborne. The continuous supply of air is produced by the forward motion of the aircraft, which results from jets or propellers that push air backwards. When the engines push air back, the air is in turn pushes the engine and plane forward. We will learn later how the curved surface of an airplane wing enhances the lifting force. Concept check. How do you identify the action-reaction forces in an interaction? 7.5. Defining systems. An interesting question often arises. Since action and reaction forces are equal and opposite, why don't they cancel to zero? To answer this question, we must consider the system involved. Consider, for example, a system consisting of a single orange, as in figure 7.10. The dashed line surrounding the orange encloses and defines the system. The vector that pokes outside the dashed line represents an external force on the system. The system, that is, the orange, accelerates in accord with Newton's second law. Note, a system may be as tiny as an atom or as large as the universe. 7.10. A force exerted on the orange, and the orange accelerates to the right. So that's the system. Everything surrounded by the dotted line is a system. In figure 7.11, we see that this force is provided by an apple, which doesn't change our analysis. The apple is outside the system. The fact that the orange simultaneously exerts a force on the apple, which is external to the system, may affect the apple, another system, but not the orange. You can't cancel a force on the orange with a force on the apple. So in this case, the action and reaction forces don't cancel. Action and reaction forces do not cancel each other when either of the forces is external to the system being considered. Figure 7.11. The force on the orange provided by the apple is not canceled by the reaction force on the apple. The orange still accelerates. Now let's consider a larger system enclosed both the orange and the apple. We see the system bounded by the dashed line in figure 7.12a. Notice that the force pair is internal to the orange apple system. Therefore, these forces do cancel each other. They play no role in accelerating the system. A force external to the system is needed for acceleration. That's where friction with the floor comes in, as in figure 7.12b. When the apple pushes against the floor simultaneously pushes against the apple. An external force on the system. The system accelerates to the right. Inside a baseball are trillions and trillions of interatomic forces at play. Here's figure 7.12. Consider the largest system of orange plus apple. A. Action and reaction forces cancel. B. When the floor pushes on the apple, reactions to the apple's push on the floor. The orange and apple system accelerates. Ponder this figure very carefully. I'll let it run for 5 seconds or so. They hold the ball together but play no role in accelerating the ball. Although every one of the interatomic forces is part of an action-reaction pair within the ball, they combine to zero, no matter how many of them there are. A force external to the ball, such as a swinging bat provides, is needed to accelerate the ball. If the action-reaction forces are internal to the system, then they cancel and the system does not accelerate. Consider the football in figure 7.13a. There is one interaction between the foot and the football, and the ball accelerates. But when two kicks act on the ball, as in figure 7.13b, no acceleration occurs. In this case, there are two interactions occurring. A football is kicked. A. A acts on B, and B accelerates. B. Both A and C act on B. They can cancel each other, so B does not accelerate. If the two kicks on the ball are simultaneously equal and opposite, then the net force on the ball is zero. It is important to notice that the opposing forces act on the same object, not on different objects, so they do not make up an action-reaction pair. Why don't action-reaction forces cancel each other? Suppose a friend who hears about Newton's third law says that you can't move a football by kicking it because the reaction force by the kicked ball would be equal and opposite to your kicking force. The net force would be zero. So no matter how hard you kick, the ball won't move. What would you say to your friend? Tell your friend that if you kick a football, it will accelerate. No other force has been applied to the ball. What are the reaction forces? Aha. That force doesn't act on the ball, it acts on your foot. Tell your friend that you can't cancel a force on the ball with a force on your foot. 7.6 The horse cart problem. A situation similar to the kick football is shown in the comic strip Horse Sense. Look at figure 7.14. Here we think of the horse as believing its pull on the cart will be canceled by the opposite and equal pull by the cart on the horse, thus making acceleration impossible. This is a classic problem that stumps many college students. By thinking carefully, you can understand it. The horse cart problem can be looked at 3 different points of view. First, consider the point of view of the farmer who is concerned with getting his cart, the cart system, to market. Then, there is the point of view of the horse system. 7.14 All the pairs of forces that act on the horse and cart system are shown. The acceleration of the horse cart system is due to the net force of the applied force and the frictional force. So you have a net force that is actually pulling the horse cart system to the right. Finally, there is the point of view of the horse and cart together, horse cart system. From the farmer's point of view, the only concern is with the force that is exerted on the cart system. The net force on the cart divided by the mass of the cart will produce a very real acceleration. The farmer doesn't care about the reaction on the horse. Now look at the horse system. It's true that the opposite reaction force by the cart on the horse restrains the horse. Without this force, the horse could freely gallop to the market. This force tends to hold the horse back. So how does the horse move forward? The horse moves forward by interacting with the ground. When the horse pushes backwards on the ground simultaneously pushes forward on the horse. If the horse in the horse cart system pushes the ground with a greater force than it pulls on the cart, there is a net force on the horse, and the horse cart system accelerates. When the cart is up to speed, the horse need only push against the ground with enough force to offset the friction between the cart wheels and the ground. Finally, look at the horse cart system as a whole. Think, what is the net force that acts on the cart in figure 7.14, on the horse, on the ground? The net force on the cart is P and F, on the horse is F and P, and on the ground is F and F. I leave you to figure out what is capital P, capital F, small f, etc. relative to the drawing. From this point of view, the pull of the horse on the cart and the reaction of the cart on the horse are internal forces, or forces that act and react within the system. They contribute nothing to the acceleration of the horse cart system. They cancel and can be neglected. To move across the ground, there must be an interaction between the horse cart system and the ground. For example, if your car is stalled, you can't get it moving by sitting inside and pushing on the dashboard. You must interact with the ground outside. You must get outside and make the ground push your car. Horse sense. Giddy up, pull the cart so we can get going. For me, to pull the cart would be a futile effort. You see, if I pull on the cart will push back on me. By Newton's third law, the forces are equal and opposite, so they'll cancel out. A zero net force won't get us moving. Acceleration of the cart equals the force on the cart divided by the mass of the cart. I don't care about the force exerted on you. I'm interested in the force you exert on the cart. You pull the cart, and I guarantee it will move. But how can I move forward when the cart pulls backward on me? Curious. Just push backwards on the ground. By Newton's third law, the ground will push forward equally on you. Then I'll simply follow along. That ground is doing a good job. The horse cart system is similar. It is the outside reaction by the ground that pushes the system. How does a horse cart system accelerate? 7.7 Action equals reaction. This chapter began with a discussion of how a wall pushes back on you when you push against it. Suppose that for some reason you punch the wall, bam, your hand is hurt. Look at the cartoon in figure 7.15. Your friends see your damaged hand and ask what happened. What can you say truthfully? You can say that the wall hit your hand. How hard did the wall hit your hand? It hit your hand just as hard as you hit the wall. You cannot hit the wall any harder than the wall can hit you back. Hold a sheet of paper in midair and tell your friends that the heavyweight champion of the world could not strike the paper with a force of 200 newtons, 45 pounds. 7.15. If you hit the wall, it will hit you equally hard. You are correct, because 200 newtons interact between the champ's fist and the sheet of paper in midair is impossible. The paper is not capable of exerting a reaction force of 200 newtons, and you cannot have an action force without a reaction force. Now, if you hold the paper against the wall, well, that's a different story. The wall will easily assist the paper in providing 200 newtons of reaction force, and more if needed. For every interaction between things, there is always a pair of oppositely directed forces that are equal in strength. If you push hard on the world, for example, the world pushes hard on you. If you touch the world gently, the world will touch you gently in return. Concept check. What must occur in every interaction between things? Let's look at the summary. Newton's third law, action, reaction. A force is always part of a mutual action that involves another force. Newton's third law states that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. To identify a pair of action-reaction forces, first identify the interacting objects A and B, and if the action is A on B, the reaction is B on A. A given force exerted on a small mass produces greater acceleration than the same force exerted on a larger mass. Action and reaction forces do not cancel each other when either of the forces is external to the system being considered. If the horse in the horse cart system pushes on the ground with a greater force than it pulls on the cart, there is a net force on the horse, and the horse cart system accelerates. For every interaction between things, there is always a pair of oppositely directed forces that are equal in strength.